So hi, IVA attenders. I'm Chaona Chen, and I'm a postdoc researcher working at the Face Syntax Lab at the University of Glasgow. Today, I will present the work from our lab where we use human perception to build culturally valid dynamic facial expressions for a conversational agent. And first of all, I want to thank all of my co-authors and founders for supporting this work. Conversational virtual agents are designed to engage in daily conversations with their human users. To do so, they must be equipped with an essential repertoire of social signaling capabilities to guide the flow of a conversation. Now, facial expressions are frequently used by human users across all cultures to facilitate the flow of a conversation. For example, when the listeners show facial expressions of thinking, the speaker may pause and wait. When the listeners show a facial expression of confused, the speaker may rephrase what has been said. Similarly, the speaker may decide to change a topic or continue a topic when they see a different facial expressions of bored or interested. Despite this central role in daily conversation of these facial expressions, relatively little is known about which specific face movements actually convey such conversational messages and whether they are sufficiently similar across cultures to support successful cross-cultural communication. One of the reasons making it challenging to understand such facial expressions is because the face is a highly complex dynamic information space. Now, human face comprises different individual face movements, which we called action units, as some of them are showing here. And also, it can be the combination of these action units with different dynamics, for example, with low and high, if different intensity level, early or late peaks, or even slow and fast peaks. So due to the knowledge gap in the conversational facial expressions, even the most state-of-the-art virtual agents are often equipped with a very limited range of facial expressions. For example, this is a very popular 3D virtual agent called Furhat, and it can only display a small set of facial expressions, such as happy, surprise, fear, disgust, anger, and sad. And you can notice that they are quite static because they don't actually have the natural dynamics as the human faces. More importantly, these facial expressions are actually based on Western-centric approaches. So recent study has been shown that these facial expressions are not well recognized across other cultures. Therefore, we aim to address this critical knowledge gap with a twofold aim. First, to advance understanding of these conversational facial expressions by precisely modeling their face movements in two distinct cultures, Western Europe and Eastern Asia. Secondly, we want to transfer these culturally sensitive facial expressions to a conversational virtual agent to see if they can be recognized. So to do that, we use a psychological data-driven approach. The main idea of this approach is very simple. For example, we present this facial expression to participants and let them choose what they think it shows. For example, as a participant, you may think that this shows something negative, such as disgust. And for this one, you may think that it may not meaning anything to you, or you are not sure what it means. So the fact is that all these facial expressions are randomly generated. This means that we do not pre-assign any meaning to these face movements and only derive the meaningful facial expression based on human perception. Let me explain this with more details. First of all, to generate these random face movements, we use a dynamic face movement generator that developed by Yu and his colleagues. It contains a library of over 40 action units that can precisely control the movement of each action unit. Some of the example of these action units, as you can see here. And we can precisely control, for example, how strong and how fast it peaks, at which time it peaks, and so on. And then, therefore, by controlling and combining these action units, we can then almost generate any facial behavior. So on each experimental trial, the generator randomly selects a set of action units. It can be any number between 1 to 5 action units. For example, in this particular trial, the generator randomly selects these 3 action units. And for each action unit, the generator also assigns a random phase movement using the 6 temporal parameters, including peak amplitude, peak latency, offset, onset, acceleration, and deceleration. And these randomly select action units are then combined to create a facial animation. So the observer then viewed this facial animation and categorized it according to a set of key conversational messages. For example, we use the thinking, interest, bored, and confused in this experiment. If and only if that the participants think that the dynamic facial expression conveys this particular conversational message. Otherwise, they will select other. Therefore, by doing so, we can capture the specific face movements that elicit the perception of a conversational message to this individual participant in a given culture. After many such trials, we can therefore build a statistical relationship between the stimulus information and presented on each trial and the observer's responses. We can then produce a mathematical model that represents each conversation message to each individual participant. This means that we have a precise, quantifiable representation of the dynamic action unit patterns that can be objectively analyzed and directly transferred to the virtual agents. So using this approach, we modeled the facial expression of our 4 conversational messages in 20 Western and 20 Eastern Asian individual observers. We then transferred these models to a popular 3D virtual agent called Furhat. Specifically, we supplemented the agent's existing face movements vocabulary with the set of 42 action units and displayed each facial expression model on a new set of same ethnicity face identities. We used a perceptual discrimination task with a new set of 20 participants per culture. On each experimental trial, the participants viewed one of the 4 conversational messages, for example, confused, followed by a facial expression. And participants indicate whether the facial animation correctly or incorrectly matched the label. We randomized all the trials within the experiment and counterbalanced the response keys across participants. So following the experiment, we computed the hit rate and false alarm rate for each facial expression model and each culture separately. Specifically, high hit rate means that the facial expression model is correctly characterized with the matched conversational message. In contrast, high false alarm rate would mean that this facial expression model is incorrectly characterized with the mismatched message. Therefore, we divide the performance of the 4 facial expressions into these 4 types of performance according to their hit rate and false alarm rate. Here, the color-coded circles shows the results of Western facial expression models, where the colors representing the 4 different conversational messages, as shown here. And the triangle here shows the result of Eastern facial expression models using the same color coding for the conversational messages. So we can see that the majority of our models, except some of the board and thinking models, that are actually performed very well on a Furhat. So to further test the validity of these facial expression models, we ran a separate study where we displayed each facial expression model on a flat screen and tested with a new group of 20 participants per culture. And the results of the on-screen display are shown here using the hollow shapes. Again, so the results show that the majority of the facial expression models are in this first quadrant, no matter they are displayed on a 3D virtual agent or a computer or on a computer screen. Now, next, To understand which specific action unit patterns conveys these conversational messages in each culture, we extracted the validated facial expressions in both studies and then presented the distribution of the action units using these color-coded face maps. With warmer colors shows more consistency across the models within each culture. So that we can see that, for example, in both Western and Eastern Asian interests, the facial expression, that they share the same action units as raising eyebrows and a very opened smile. And interestingly, we see that thinking facial expressions has relatively lower consistency even within the same culture, which means that even in a same culture that everyone seems to have a different idea of what facial expression of thinking should look like. And we see differences in between the culture for the facial expression of confused, where it seems there's differences in their mouth movement. So to formally examine the cultural similarity and differences in these conversational facial expressions, we identify the specific face movement. Here, what we mean by action units that are common and across cultures, and those that are specific to each culture, using an information theoretic approach based on mutual information. Specifically, results show that lip tightener and lip presser are shared in the facial expression of thinking for both cultures, and brow raiser and lip corner puller are shared in facial expression of interest. Eyes closed and up lip raiser are shared in facial expression of bored, and bored lower and nose wrinkler are shared in facial expression of confused. We also find the cultural differences in the facial expression of confused, where Westerners use this horizontally stretched mouth movement, and Eastern nations showing this with the vertical mouth stretch. So this is cultural differences in showing the facial expression of confused. Now, so far, we have shown that we derived the culturally valid facial expressions for the virtual agent using our perception-based data-driven approach. We want to emphasize that our data-driven approach can be used in understanding other social signals displayed on the face. For example, how different gaze pattern or different head movements would elicit different conversational messages, and even can go beyond the social information on the face, such as the sound and the gestures. We have a few ongoing projects and collaborations for developing the multimodal social communication abilities for virtual agents. To summarize, we derived the facial expression models of the 4 key conversational messages in 2 distinct cultures using a perception-based data-driven psychological approach. And we show that these conversational messages, facial expressions, can be successfully transferred onto a conversational virtual agent. A further cross-cultural analysis of the conversational facial expressions showed systematically cultural dissimilarity and differences that could facilitate or hinder cross-cultural communication. Our results demonstrate the general power of using culturally sensitive perception-based approach to develop cultural valid facial expressions for the conversational virtual agents. And that's all. Thank you for your attention. If you have any questions or comments, please contact me via this email address or leave comments here. Thank you.